Okay, so the recording has started. All right, so today we're going to cover basically the material that was assigned to A1, L3, and L4. So that's section 6.2.9 to 6.4, or basically stationary probability of a discrete term Markov chain. And then we'll go into continuous term Markov chains, and then the birth-death process, which is 6.4. So what I'll be doing today will be to look at the exercises 11 through 15, which is what had been assigned, that had been assigned to you. And I'll go it very slowly and carefully. And if you have any questions, of course, you can stop me and so on. And if there are any concepts or issues or whatever that you find confusing in this material, just feel free to stop and raise your hand. I'll see it on the screen, and I'll be able to answer it as best I can. Okay, so that's how we're going to do this, the examples class. One more thing before I begin is that on Thursday, which will be the first assessment, it will be on the material essentially from the beginning to section 6.4. And so it will be in the form of questions that will be made available to you on Moodle. And you can choose to either do them between 10 a.m. and noon GMT, or between 3 p.m. and 5 p.m. GMT. So you have to make a choice. So when you go to the Moodle on Thursday, it will say, pick one of these choices. And when you pick one, that's the one that you have to do. So you can do it between these 2 hours. We're giving you the flexibility. And then you have, and the questions will be similar to the exercises. They are obviously not identical, but they're going to be similar. So if you can do the exercises, we should not have too much trouble with the assessments either. Unfortunately, I've been told by the department that because of the overlap between the 10 a.m. to noon time and the assessment being 10 to noon and the office hours being 10 to noon, they don't want me to hold office hours at that time. So there will not be office hours this Thursday for that reason. So if you really do want to talk to me or something, send me mail. We can try and find a time. But then we will have office hours next week, of course. There will be examples class next week as well. So again, there will be these 2 timed assessments, and you can pick this. And the other thing also is, as you probably have seen from the other units of assessment, I can't give you back your marks. You'll get a letter grade, which will give you an indication of the marks, mainly because you're going to be doing moderation in June across the different units. So but I will give you back letter grades, which will be corresponding to the marks. Okay. Any questions about that? Yeah. Okay, great. So let's get started. So I'm going to straight away go to question 11, and just for, okay, so you're just going to see the top of my head. So I'm going to stop my video. All right. Okay. So good. So for this question, we start with the Markov chain that we looked at earlier. And so let me draw the chain. So it has 4 states like this. This is because we said let's start. It's going to be, so let's call that 1, 2, 3, and 4, and they all have self loops with 0.8. So you have 4 self loops with the same. Sorry, 0.8, 0.6, 0.6, 0.8. And then the transition probabilities are essentially 0.2. All of them are 0.2 like that. And so if you write it down in the form of a matrix, this is what it looks like. The transition probabilities would look like this: 0.8, 0.2, 0, 0, 0.2, 0.6, 0.2, 0, 0, 0.2, 0.6.
Da.
Okay, so this is the transition rate matrix, and so any questions about this? This should be basically just a revision. So now to find the stationary probability, first we need to check, is the chain, is it ergodic? And so to check whether its chain is ergodic, okay, so somebody want to answer that? How would you know it's ergodic? What would you check? Yeah, Luke?
First of all, we look if it is like irreducible, and with
Yeah,
this appears to be the case.
yeah,
And
check.
yep, then we should check for um recurrency of the states.
Yeah, I mean, there's an easier test than that for finite chains.
Yes, in this case, like for every state, we there is always some probability of getting back to it.
That's right. So it's not getting back to that's irreducibility. That's you already checked. What are the other two tests that you can use that are easy, which was for finite chains? Or one more test for a finite chain?
Mm, um,
Okay, does anybody else want to jump in?
It's
Yes.
finite and aperiodic
Aperiodic. Why is it aperiodic?
because there is a self loop on every state, although like even a single self loop would have sufficed.
That's right. So it's aperiodic, and then and the other thing is it is finite. So we can just test that. So it's finite, aperiodic, irreducible. So yes, it's ergodic. If it's ergodic, then we can just use theorem 6.2. And what theorem 6.2 states basically is that if the pi j star is the stationary probability, pi j star is given by some sigma I pi I star pij. So what we're saying over here is that the steady state probability being in state J is just the sum of the probability, steady state probability being in state I multiplied with the probability of getting from I to J. So we're sort of, I want to give you a little bit of a physical interpretation of this. So we can sort of think of the steady state probability. Think of the probability. This is weird, but it actually is. It's think of it as like a water in a bucket. Okay, it's a certain amount of water that's in this bucket over here. Okay, that's the amount of probability. We call the probability mass that's present at that particular state. And so the pi ij star is sort of the probability mass in the I star in the ith state, and from that mass, we are essentially giving certain amount, this ratio we're giving back, Pij, we're going to put into the other bucket. So think of each transition as basically taking a ladle full of water of size Pij, taking that ladle full of probability and pouring it from one bucket to the other, okay, at a particular at a discrete point in time. And so at each point in time, we take these buckets of water and we take a ladle, the size of the ladle is Pij, and we're going to just pour it from one to the other. And if we are at the stationary state at the end of each transition, the levels remain the same. There's no change in the levels. Okay. And that's what this means over here. So if I have sort of this is pi, let's say pi 1 star, and then you have pi 2 star. So you're going to transfer basically P21 from here to here. We're going to transition P12 from here to here. And if you can think about it, if P12 and P21 are the same, then the probability masses don't change. They kind of stay the same, right? And the sum of the masses have to, so that's sort of intuitively speaking what the stationary probability looks like. I'm talking about this water bucket analogy because when you do continuous Markov chains, in fact, we will use this analogy. It'll become very easy to understand continuous time Markov chains using that same analogy. Okay, so when you do this, when you fit in these equations over here, the equations become basically something like this: pi 1 star equals zero 0.8 pi 1 star plus zero 0.2 pi 2 star, and then pi 2 star is going to be zero 0.2 pi 2 pi, zero 0.2 pi 1 star plus 0.6 0 0.6 pi 2 star. That's a self loop plus zero 0.2 pi 3 star, and so on. I mean, there's two more equations, and then the last one is 1 equals pi 1 star plus pi 2 star plus pi 3 star plus pi 4 star. Okay. And if you solve all of these, you basically get pi 1 star equals pi 2 star equal, they're all equal to 0.25. And you can solve them using just Gaussian elimination, or if you're feeling lazy, there are going to be you can find an online linear system equation solver. There's you can just plug in the values and it'll tell you the answer. So either way, you can get the answer. Okay. Any questions about this, Yaguk?
Is it okay to solve this numerically by iteration powers on the transition matrix?
I mean, you can solve it any way you want, of course, but it's a very straightforward straightforward set of equations, so you don't really need to go to that kind of machinery. But yeah, you could do that. Yeah. Yeah. I mean, however you solve it is up to you. As I said, it's a fairly trivial system. But in a realistic system, the fastest way to solve it would be to use used to Gaussian elimination, because you can handle very large matrices in that way, and the answers are pretty. That's what actually, if I remember correctly, that's what I did. Not for this one, but for the one in the text, I just used the online system. Okay, any questions about this? The stationary probabilities in general. So stationary probabilities of Markov chain are in some sense what we really care about. We care about them because we want to know, because we associate essentially semantics with each state. These states have meanings. When you talk to, especially when you go to birth-death processes, especially go to queuing theory, a state has a meaning. It has a number of customers. So in a continuous time Markov chain, the probability of being in a particular state is sort of the number of customers. If I want to know what's the probability there are going to be 5 customers waiting for service, that's pi 5 star, right? So these things have actual meaning. So that's why we spend so much time about it. And then now it becomes clear why ergodicity becomes interesting. It's because we can compute these stationary probability distributions only for ergodic chains. Okay, for non-ergodic chains, we're going to have more complicated issues. So the Markov property, time homogeneity, and ergodicity allow us to compute trivially the stationary probabilities, and that's why we essentially try to work as much as possible with ergodic and time homogeneous Markov chains. Okay. All right. So the next question is about residence times. So that's question 12, residence times. So it says, what are the residence times? So here's the chain again, and of course the residence time in state J is going to be given by 1 over 1 minus BJJ. So that's the self loop. So the residence times are going to be 1 over 1 minus 0.8 for states 1 and 4, which is 5. And then for the others two states is 1 over 1 minus 0.6, which is 2.5. So this is the expected residence time in states 1 and 4. That's not a very repetitive. Okay. So state 1 and 4, and for state 2 and 3. Okay. Should be straightforward. Okay. Any questions? All right. So let's move to question 13. So now we're going to continuous time Markov chains. And, I find it confusing, and other people find it confusing. When you go to discrete continuous Markov chains, we actually, the matrices we work with are not the same matrices, right? We are not talking about the transition rate matrix. We're not looking at the transition probability matrix, the transition rate matrix. So let me give you a little bit of intuition over here. So remember that we had sort of this bucket of water analogy. This is a probability mass, and that's let's say these are 2 states, state 1 and state 2. And I have a kind of a pipe that's going between them, and the pipe sort of flows in that direction, right? Then I have sort of a rate at which the water is flowing from one pipe to the other. Okay. In the discrete time case, I have a ladle, right? I have a discrete time. At that time, I transfer all the mass over, right? In the continuous time, I'm going to transfer this at the rate Qij, or in this case, Q12. So Q12 is the rate at which the water, the probability is flowing from 1 to 2, and symmetrically, the water is flowing at the rate q to 1 to go from 2 to 1. And you can, if you interpret the equations for this, so the equations on page 254, you will see that this is basically how all of them work. So Qij, for example, is the limit as delta t tends to 0 of pi, oops, whoa, what is that? Okay, then the t tends to 0. I'd better be careful with this. Okay, Pij delta t over delta t. So essentially it's saying over the time period delta t, how much mass am I transferring? That's Pij, okay? That's how much mass I'm transferring divided by the time period. And of course, that's the rate, right? That's the definition of velocity. If you look at the distance, if you remember how you can compute velocity from distance, velocity is the rate of change of distance. Here, Qij is the rate of change of probability across these time periods. And so, so this is the way we can think of Qij, and then Qjj, which is the self-loop probability, is defined as minus sigma sigma j Qij. So it's all it's a sort of a technical thing we put in. It has no specific meaning. We just put it in so that the rates sum to 0, and so it's sort of a it's not. It doesn't have physical interpretation. What do you mean by negative transition rate? It doesn't mean anything. It's just something we keep to so that the math is easier to solve when you do it this way. At least that's one way to understand it. So the equations in 254 are for essentially arbitrary continuous time Markov processes. And we'll first look at those, and then we look at the specific birth-death process. So for equation 13, the what we have over here is the is this process. So let me write down this is a continuous time process, and I'm writing over here not the transition probabilities, but the transition rates. And so here's the transition rate from here's 2, this is 2, 4, 4. And this is a particularly kind of a simple, but process, but also continuous time Markov chain, where the rate at which probability mass is leaving is the same as the rate at which it arrives. Basically, that's what we're showing over here. So from each state, the arrival and departure rates are the same. So if you write down so the first part is what's the similarity and difference between this and the the discrete time process. So here's a discrete time Markov chain, right? So can somebody talk about the similarities and differences between the two? Anybody want to try? Well, what's similar? Okay, I'll pick somebody. Okay.
We still have discrete states.
Yeah.
And there might not be like an edge between two states, but
right.
Instead of having like discrete distribution that at each time step determine next state, we have like departure rates or transition rates.
That's right. So it's in both cases we have a directed graph, right? And we have in both cases we have the possibility of finite or infinite number of states. But the edges are marked not by the transition probabilities, but by the transition rates. So that's a major difference. And of course, in the case of the of a discrete change over here, all the probabilities along the rows, these ones over here, have to sum up to 1, which is by saying that all the probabilities that that leave a state have to sum up to 1, right? So these have to sum up to 1 because you have some probability of going somewhere else. So all including the self loop, the total probabilities are to sum up to 1. Here, of course, there's no such thing. The rates don't have any kind of probability associated with them. They're the limiting rates at which probabilities are transition. Okay. Okay, so now let's write down the transition rate matrix. So the second part of this question is what's the Q matrix? So the Q matrix is going to be given by this. So we have essentially you can write it down in various different ways, but the easiest way is you can say, well, that's a birth-death process. So from equation 619, we can just write this down as minus 2, 2, 0, 0, 2, minus 6, 4, 0, 0, 4, minus 6, 2, and 0, 0, 2, minus 2. So that's the Q matrix over here. Pretty much by inspection from, by looking at what are the lambdas and mu. So this is minus lambda 0, this minus lambda 1, minus lambda plus mu. So, sorry, yeah, minus mu, minus lambda plus 1 plus mu 1, and then that's lambda 1, and so on. So we can just write it down given the lambdas and mu's, right? So this is, okay. So maybe I should just annotate this. So the rate of departure from here is going to be mu1, and the rate of arrival from here is going to, this is, sorry, this is, what am I doing? Sorry. Yep. This is lambda 0 over here. Transition rate is lambda 0, and this is going to be mu1. This is lambda 1, lambda 2, mu1, mu2, mu3. Okay, so mu is the rate at which we depart state 3. So mu3 is the rate at which we depart state 3, mu2 and mu1, so on. And lambda is how is the arrival rate when we are at 0 to get into 1. So that's how the lambdas and mu's come in, and to get the Q matrix over here. Okay, any questions about this? Okay, so now what we want to do is to compute the steady state transition probabilities for this chain. And the way to do it, the way I was hoping we would do it was to use equation 613 for it on page 254. So equation 613. And that tells us that for a continuous state Markov chain, the equations are Qjj pi j star plus sigma k not equal to j q k j by k star equals 0, and then sigma j by j star equals 1. So the first one says at the steady state, right? This on the right hand side, this stuff over here is sort of the rate at which probability is entering into state j. Okay. So you're saying that you're at state k, so pi k star is the amount of water in k, and then qkj is the rate at which is coming into j. So we sum it across all the different pi k's, all right? And that's the total amount of kind of water coming into a probability mass coming into state j. And then qjj is sort of the, as I said, if we write it down properly, this just can be thought of as being the exit of the probability mass over here. So this is just to balance things out, but this has a physical interpretation, this really doesn't. But then we're saying that the total amount of change due to this is 0, right? We're not having any change because it's stationary. It looks like it hasn't changed at all. So that's stationarity in the discrete sense means that even though time has gone past, if I'm in the stationary state, I stay in the stationary state. In the continuous time, similarly, if I'm in the stationary state, I don't exit the stationary state. That's my sort of what the chain is expected to be doing in the long run. And if we now substitute this over here, we get the equation. Whoops, let me go back to this. So minus 2 pi 0 star plus 2 pi 1 star equals 0. 2 pi 0 star minus 6 pi 1 star plus 4 pi 2 star equals 0. 4 pi 1 star. And then finally, sigma pi I star equals 1. And then again, this is a linear equation, systolic linear equations. And if you solve all of them, you'll get pi 1 star equals pi 2 star. It's basically all going to be 0.25. Okay. And so this is again simply from equation 630, basically plugging it in and solving it. Okay, any questions about this? Okay. All right, so let's move on to the Poisson process is what's called a pure birth process, and the opposite of a Poisson process is called a pure death process. So in a Poisson process, we start at state 0. Sorry, let me draw this properly. So so we don't have any death arrows. We just have birth arrows, and they're all at the same rate lambda. Okay, that's what a Poisson process is. And so it has an infinite number of states. So the probability of it being in a particular state j, so pi j star, is essentially the same is the probability of having j arrivals into the system starting at state 0. So at time 0 is state 0. How many probabilities, and this is given by, and the reason we call it Poisson process is because this probability is in fact the exactly the Poisson probability, which is pi j at probability of j arrivals in time t is lambda t to the j by j factorial e to the minus lambda t, which is the standard Poisson Poisson. Now, another way of thinking about the Poisson process, which you may or may not know, but is certainly useful to think about, is that what the Poisson process is saying is that at every state, we have a rate of arrivals, which is lambda, right? So remember now, think of the transition rate as being this flow of probability, right? Okay, so the flow of probability is a continuous drip of probabilities coming in at the rate lambda. So imagine that you have a pipe, and in that pipe you have water, which is probability water, probability mass water, and it's dripping in, and the rate at which it's dripping in is lambda. It's always lambda. No matter how much is in the bucket, it's always coming in at lambda. Okay. What we want to know is the expected size of the bucket. How many drops of water are in the bucket at any point in t? And that is exactly given by this equation, the Poisson equation. All right. So the Poisson process characterizes any system where we have a continuous and time-independent arrival rate, probability of arrival rate at any time interval. So no matter how, if you have time interval of time t, then the total amount of probability dripping in or total amount of stuff dripping in is lambda t. So the rate of the lambda, the infinitesimal rate is lambda, and then the obviously if you have time duration t, then the total amount of accumulation is lambda t. Okay. So the history of the Poisson process is interesting. I don't know if does anybody know where the Poisson process comes from? Where is it?
Is it by taking the limit of repeated exponential, like drawn in like small times, right?
Well, that's one way of doing it, but the historical idea is actually weird. So if I know, if I remember correctly, Poisson is the name of a French mathematician, and he was looking at how many people got killed by mules in the French army. Okay, why would they get killed by mules? They were standing, they're bending down next to a mule, and the mule kicked them, and they died. And this happened, I don't know, 1700s, something like that, in the French army. I guess, I don't know if it's Napoleon army or not. And he saw this amazing pattern, which is that the probability of getting kicked by a mule is fairly low. But if you take that and you average it out, the number of mule deaths was exactly given by by this distribution over here. And it can be modeled as every time you're next to a mule, you have an infinitesimal drip of probability of getting kicked by the mule, right? And if you have enough people who are next to enough mules, it all averages out, and somebody's going to get killed. One of these soldiers is going to get killed by the mule. And so he found that that was the origin of a number of mule deaths due to a number of deaths due to mules in the French army. And then he started seeing this pattern over and over again. And of course, now we view it as being this continuous steady drip of Poisson fluid, of probability fluid. and into a receptacle essentially, which is accumulating it, right? Okay, does that make sense? Yeah. Okay. All right. So let's now look at a pure death process. The pure death process is sort of the opposite. So we have a certain population, which is the initial population, and we are only going to leave over here in this way. And we're going to leave it at some particular rate, mu. And so that's sort of the death process. So your population and everybody has a certain probability of dying, and it's infinitesimal, but it's accumulated, suddenly somebody dies and then the population reduces and so on and so forth. And the death rate is independent of the population size, right? It doesn't matter whether you're 1,000 people or not, it's, or 1,000,000 people, the death, the total amount of death probability is independent of population size, okay? So that's what's going on over here. And the question is sort of prove that that the resistance time is exponentially distributed. I mean, all you need to do is to say this is a continuous time Markov chain. And just because it's continuous time homogeneous and Markov chain without history, residence times are exponentially distributed, basically by definition. Okay, that's true for all of them. So if you look at section 6.3.2 on page, where did I put it now? On page 253, it just says residence times exponentially distributed for continuous time Markov chain. It's the same reason, because basically when you're sitting in that state, you don't know when you're going to depart. It's a memoryless process. The memorylessness is coming from the Markov property, right? The Markov property essentially says you don't know the past history. You don't know when you arrived at the state, right? You can forget about all the past history, and the transition probability is independent of past history, including the amount of time you spent in the state. And because you don't know that, it must be the case that the time spent in the process, in the state, I'm sorry, is exponentially distributed, sort of by definition of the Markov property. And so if it's Markov, it's a continuous death process, therefore it's exponentially distributed. So it's sort of it's not a very tough question. It just makes you think a little bit about what's going on. Okay, so Luke, does that answer your question here? Okay, all right. Okay, let's move on to the next one, which is the stationary probability of a birth death process. So here we're going to compute the same stationary probability, but we're going to use equation 630 to do this. So equation 630, which is on page 261. What we're saying over here is that so here what we do is we're saying, okay, we're going to find the transition probabilities for specifically a birth death process. And here we start like this. We say pi 1 star is going to be lambda 0 by mu 1 by 0 star. And then pi 2 star is going to be given by lambda 0, lambda 1 by mu 1, mu 2 by 0 star, and so on. So basically multiplying the numerator by lambda 0, lambda 1, and denominator by lambda mu 1, mu 2, etc. But if you look at this chain over here, this is a very simple chain. The lambda I is going to be is equal to mu I plus 1, right? So that's what we see. So when you go out at 2, you come back in at 2. You go out at 4, you come back at 4. Go out at 2, come back at 2. And so if you do that, it's basically you can just by looking, you can see that pi 0 star is equal to pi 1 star equal to pi 2 star equal to pi 3 star, etc. Right? These are all going to be the same. Why? Because these two cancel out. So pi 1 star is pi 0 star, and then the same holds true. So they're all going to be the same. They're all the same, and they sum up to 1 equals 1. That means that pi I star for all I equals 0.25. Right? And in fact, that's exactly what we saw earlier. Pi I star is 0.25. And so we just got it two different ways. One is solving the kind of the full Q matrix, right? And the other one is just saying, well, I don't really need to look at the Q matrix if I know it's a birth death process, because I can just use equation 630 essentially to do it. Okay, so that pretty much finishes the exercises for this part of the course. So Okay, so are there any questions or anything in the text that you'd like me to answer now? Yes,
I
Vinay?
had one question.
I think Vinay was first. I'm
Oh,
sorry.
okay.
Yeah.
Yeah.
Yeah. Go ahead, Vinay.
Yes, my question is, if we have a solution for the equation for the stationary probability distribution, does this mean that our chain is ergodic?
I see. Does the solution imply ergodicity? It's I would say that we shouldn't jump to that conclusion, right?
Okay.
There are always pathological cases. It's like saying if I have it's like saying if I have a cart, is there a horse, right? Normally, you're putting the cart before the horse. So uh, ergodicity is necessary to compute the stationary distribution, but I can't think of it at the top of my head, but I could imagine that you could come up with a pathological case where there is a solution, but there isn't ergodicity. Yeah, Luke, you have a...
If you have just two states and each state just goes into the other, you have a cycle of length 2.
Yeah.
But you could say that like half and half is like stationary distribution, right?
Okay.
Multiply by the transition matrix, it stays the same.
Yeah, but I mean, as you're saying, that's a periodic one.
Also, we're assuming
Also,
given that it's periodic.
for two states, I think you can easily compute the recurrent value. If you can compute if it's recurrent null or recurrent not null, because
that's right.
You'll cycle in state 2 for n states, and then you go back to 1.
Yeah. So again, I would hesitate. It might be true. I'm going to write it down, and I'll see if I can think through it. But I would hesitate to give you an answer right away. So does solution to stationary problem. Okay. Let me look into that. Okay, and then Vasundhara, you had a question?
Yeah, my question was, say if you're considering pi 5 star, does that mean we have 5 jobs in the queue or 4 jobs in the queue and 1 being served? Like, how are we interpreting that?
Yeah, so for the moment we are not interpreting it, right? I mean, for the moment we're just saying this is a birth-death chain. When you go to queuing theory, then we would interpret pi 0 star as the first job which is currently in the queue. So 0 meaning 0 in the queue, 1 in the one in. I'm sorry, I should take it back. Let me be careful here. So 0 would mean nothing is being served, the system is idle. 1 means 1 being served, the remaining are, there's nothing in the queue. And then 2 means 1 in the queue, and 3, etc. So basically the pi j star means j minus 1 are in the queue and 1 is being served.
Okay, thank you.
Sure. But we'll talk about that when we do the MM1 queue and so on. Yeah. So I should just add that the queuing theory, is sort of a subclass of birth-death processes. Okay, because queues arrive and depart, and birth-death processes sort of a subclass of continuous time Markov chains, where you have arbitrary transition probabilities possible in the continuous time Markov chain, and continuous time Markov chains are a subclass of continuous time chains, which are not Markov. You may have time-dependent probabilities. So we have sort of the whole space of non-homogeneous chains. Then we get the, a non-homogeneous Markov. And then you have even the worst one is non-Markov, where it's the transition probabilities depend not only on time, but they also depend upon, we cannot, on history. So I can have to know both the history and the time. That's the worst one. It gets easier when you say, okay, it depends on time, but not history. That's Markov property. Then it says, okay, it depends on time, and I don't have any dependency on time or history, and I'm transitioning just to my neighboring states. That's a birth-death process. And then, so then that's where queuing theory basically is this fairly restricted thing. But, the mathematicians they work with much more general systems, which are way more complex to analyze. Any other questions? Okay, so I'm not hearing any. So I will therefore stop the recording and send out a link to the recording on the Moodle link, and then just stopping it now.